Hey everyone, welcome to the SCM Analytics YouTube channel, your go-to place for all SCM related analytical use cases. This is Vicky here, your host of this video, and today we will be using the PuLP Python package to solve the workforce planning problem we discussed in the previous video. Let's get started. A quick recap of the problem. ABC Cosmetic Company wants to schedule the staffing for its fulfillment center. The management's objective is to schedule the work time of the DC workers to minimize the cost of providing a level of service specified by the management. The following data is provided to us. There are two types of workers, full-time and part-time. There are a total of 4 shifts, and for each shift we are given a minimum number of workers required. For each shift, we need to have the number of full-time workers to be greater than or equal to twice the number of part-time workers. The full-time workers work for 8 consecutive hours and are paid 14 euros per hour. The part-time workers can be hired for any 4-hour shift and are paid 12 euros per hour. I recommend the viewers to check out the previous video mentioned in the link below to get a more context of the problem and how we solved it using the Excel spreadsheet model. The optimal results of the decision variables are highlighted here in the yellow fields. These variables lead to a cost of 1728 euros per day to run the fulfillment center. Let's now look at the Python code for solving a problem of this nature. First step is to download the PuLP package and import the necessary package. The next step is to create the decision variables, which are the workers per shift. We know that the full-time workers have 3 shifts of 8 hours each, and the part-time workers have 4 shifts of 4 hours each that we can fill in for. These 7 variables constitute the decision variables to find the objective function. The 7 variables are full-time workers between 8 a.m. to 4 p.m., full-time 12 p.m. to 8 p.m., full-time 4 p.m. to 12 a.m., part-time 8 to 12 p.m., part-time 12 p.m. to 4 p.m., and part-time 4 p.m. to 8 p.m., and part-time 8 p.m. to 12 a.m. Next, we divide the workers per shift according to the nature of the worker's job, full-time workers and part-time workers. Here, the fields mentioned in this list are corresponding to the shifts for the different type of workers. These variables will be used in the later stage to create the total times constraint, which is the number 2 constraints given to us. The next input that is given to us is the minimum number of workers we require for the 4 shifts, which are 6, 8, 12, and 6. We then have the full-time wage and the part-time wage, which is nothing but 112 euros for the full-time worker, which is 8 into 14 euros, and part-time wage is 48 euros, which is 4 hours into 12 euros. We then define a dictionary here with the same fields mentioned in the workers per shift decision variable list. This is very important because later in the later stage when we build the linear programming model, we will reference to these keys to create the equations. Here for the first 3 variables or the first 3 keys, we assign the full-time wage, which are the shifts corresponding to the full-time workers, and the next 4 are the part-time wages. Similarly, we know there are 4 shifts and a full-time worker could be part of 2 shifts as they work for 8 hours. This given data which we showcase in this manner in the spreadsheet model is conveyed in dictionary in this format, where first of all we create 4 dictionaries corresponding to each shift with the same keys as the one mentioned in the decision variable list, and assign 1 and 0 to show the shift covers. In the first shift between 8 to 12 p.m., we know that a full-time worker working on the 8 a.m. to 4 p.m. slot can work, and a part-time worker working between 8 a.m. to 12 p.m. can work. In the second shift, correspondingly, a 8 a.m. to 4 p.m. worker can work, and a full-time worker working between 12 p.m. to 8 p.m. can work. This leads to a total entries of ones in the first two keys of the full-time workers and a part-time worker corresponding to the shift that we are talking about. Similarly, we fill for the third shift and fourth shift. Now let's look into constructing the math problem. We define the LP problem as workforce planning problem, and our objective is to minimize, which is mentioned by passing in the LP minimize variable. A dictionary called workers per shift vars is created, and all the keys in the workers per shift vars correspond to as an linear programming variable or the decision variable which we will solve. By specifying 0 in the third argument, we basically assign the lower bound value to be 0. The first step is to add the objective function to the linear programming model. We use a new function called LP sums of the PuLP package to create the objective function. We iterate through the decision variable list, which contains the different keys which we pass to the cost and workers per shift variable. The workers per shift is a linear programming variable of the PuLP package which can be referenced using the keys that are mentioned in the workers per shift list. Similarly, the cost dictionary provides us the wage for the different keys that we will pass. For example, the first key that we would pass is the full-time wage of for 8 a.m. to 4 p.m., which is 112 euros, multiplied into the linear programming variable or the decision variable, which is mentioned here. We call this objective function as total cost of workers per shift. This objective function has to be minimized, and that's why that's what is required by the management, and we call this LP minimize problem. The next step is to add the first constraint of minimum workers per constraint. Since we are constructing different dictionaries containing the keys for as reference, we iterate through the decision variable list for each key and assign and create the equation. Here, the linear programming variable will be summed based on the for list, and for the entire equation, we will say it has to be greater than or equal to the first shift constraint, which is 6. Similarly, we create the other 4 quarters respective constraints. For the total times constraint, we follow a similar procedure where we again use the LP sum variable function, LP sum function, and iterate only through the full-time worker shift and part-time worker shift. If you remember, we create two lists containing only the keys or the items related to full-time and part-time. We iterate through the list and only call the corresponding workers per shift variables, which are the LP variables for the given full-time and part-time workers. With this, we multiply the total times factor to create the total times required constraint. With this, we create the objective function, the decision variables, the different parameters that is given to us, and the two constraints. We write the LP problem as person scheduling, which we will go through before running the code. We solve for the problem, print the status to see what sort of results we get, whether we get an optimal result or not, and print the different variables, which are the number of workers we finally decide to hire, and the total cost to operate the center. If you see here, first step, we have told the model to minimize the total cost per workers per shift, which is nothing but the cost multiplied with the different shift variables. And then we create the different constraints that we see in the Excel sheet or that's given to us by combining the different shift requirement and the workers requirement. Now let's run the code to observe the results. When we run this code, we see we get an optimal status, which means the problem has been solved optimally, and we get the same cost as the one that we see in the Excel model, which is 1728 euros per day to run the fulfillment center. And if you observe closely, these decision variables have the same output as the one we see in the Excel spreadsheet model. I hope this video gave you a flavor of solving a bit more complex linear programming model using Pulse package. The first video where we solved the advertising mix using the Pulse package, we could directly create the constraints and the different sort of linear programming variable because there were very few of them. This is a real world example where we had to use LP sum because we had more than a few, one or two maybe, decision variables to solve for. That's all for today. The contents presented in this video is available in the description below. Thank you for watching. I hope this video was useful. Please subscribe to the channel and click on the bell icon for updates on future videos. Until then, take care, bye, and happy learning.